All right, let's dive right into this explainer. When we're streaming our favorite shows or running massive new models on our phones, we rarely ever stop to think about the physical machinery making it all happen. It's just the cloud, right? Well, today, we're going to pull back the curtain and look at the massive, heat-generating physical beast that the modern cloud actually is. And more importantly, we're going to explore exactly how artificial intelligence is stepping in as the ultimate cooling mechanism to keep this whole infrastructure from literally melting down. To really grasp the scale of the problem we're facing, we need to talk about a specific number, 1,000. By 2026, global data center electricity consumption is projected to absolutely skyrocket to 1,000 terawatt hours. Now, to put that into perspective, that is more than double the estimated 460 terawatt hours that were consumed back in 2022. The incredible rise of resource-intensive applications, things like edge computing, cloud infrastructure, and, ironically, AI itself, is putting a massive, unprecedented strain on local power grids. Now, the simple solution might seem to be, hey, just let the server rooms get a bit hotter and save on cooling costs. But as you'll see, that comes with a massive, massive risk. Because heat is the absolute enemy here. Think about how cranky we get without AC in the middle of summer. Our digital infrastructure gets way worse. For every 9 degrees Fahrenheit over a server's maximum temperature threshold, the hardware failure rate jumps by 30%. Even crazier, if you run a typical enterprise solid-state drive at temperatures consistently over 70 degrees, it can literally corrupt after just 2 years. That is way short of its expected 10-year lifespan. So we're dealing with an infrastructure that generates insane amounts of heat, but absolutely cannot survive in it.
So that brings us to Section 1, predicting data center heat.
Our very first line of defense? Predictive analytics models. Instead of just reacting and saying, uh-oh, the room is too hot, data centers use these statistical and machine learning techniques to basically see into the future. They take in a massive variety of variables: ambient air temperature, weather forecasts, humidity, server load, even the equipment density. Then, models like decision trees map out sequential outcomes, while regression models look at the relationship between things like CPU usage and energy draw. Meanwhile, time series and forecast models are constantly absorbing all this data, adjusting in real time. They tell the data center precisely when and where a heat spike is going to happen, so the cooling systems can proactively target specific hotspots before it ever becomes a dangerous situation. And honestly, the results of these predictive models are pretty striking. In the industry, efficiency is measured by something called a Power Usage Effectiveness Rating, or PUE. The global average PUE has dropped from about 2.5 back in 2007 down to 1.56 today. But, and this is a big but, data centers that heavily prioritize these predictive analytics can push that rating down to an incredibly efficient 1.2 or even less. By predicting exactly when processes should be scheduled for off-peak hours, and optimizing the cooling systems dynamically, they're saving massive amounts of electricity and, crucial point here, preserving the hardware. Which naturally leads us into Section 2, the cloud scheduling problem. You see, cooling the physical room is really only half the battle. We also have to tackle job scheduling, which is the allocation of tasks to available computing resources to maximize efficiency, minimize response times, and prevent server overloads. It's kind of like an infinitely complex game of Tetris. But in this specific game, the blocks, which represent user demands, cloud tasks, and edge computing workloads, well, they are constantly changing size, speed, and priority. If the system drops the blocks in the wrong place, bam, a single server gets overloaded, temperature spikes, and it drags down the entire network. Now, for the longest time, we relied on traditional heuristics to play this Tetris game. We're talking rigid if-then rules, algorithms like round-robin or min-min. Are they easy to implement? Sure, but they rely on static models. When cloud workloads fluctuate unpredictably, these old rules completely fail to adapt in real time. And that brings us to the modern solution, deep reinforcement learning, or DRL. This is the adaptable, real-time learning power that actually has the sheer capacity to manage today's incredibly chaotic cloud environments. Let's unpack exactly how that works in Section 3, Deep Reinforcement Learning Explained. The actual process this AI brain uses to learn is known as the Markov decision process, and it basically happens in 4 continuous steps. First up, the state. The AI agent observes the current status of all tasks and server resources. Second, the action. It makes a choice. It might assign a task to a specific virtual machine, or maybe it queues it up. Third is the reward. The system gets feedback. Was that action efficient? Did it save energy or did it cause a delay? Finally, the next state. The environment updates based on whatever action was just taken. The AI repeats this loop literally millions of times, constantly tweaking its strategy to maximize its cumulative reward. It essentially learns by doing. Now, within this DRL world, you've basically got two primary flavors. On one side, there's value-based DRL, like Deep Q networks or DQN. These are fantastic for estimating the expected reward of a specific action. They're great when the options are clear and discrete. But sometimes, the cloud environment is just way too complex and continuous. That's where policy-based methods come in, like proximal policy optimization or PPO. Instead of just guessing the value of an action, PPO directly optimizes the scheduling policy itself. This makes it incredibly effective for high-dimensional, rapidly changing cloud environments where traditional value-based methods might just get totally bogged down. Moving right along to Section 4, how AI agents collaborate. Because here's the thing, the cloud isn't just managed by one giant AI brain. Instead, imagine a massive factory floor filled with digital workers. Depending on what the network needs, these workers operate in three distinct multi-agent settings. First, there's a cooperative setting, where agents share a global reward. They are actively working together to balance the load across servers so nothing overheats. Then you have a competitive setting, a pure zero-sum game. Here, agents might fiercely compete to process their specific user's workload first, ruthlessly fighting for limited server space. And finally, a mixed setting, where they have to balance both, collaborating to keep the whole system online while still competing to prioritize their own specific tasks. So you might be wondering, how does a purely competitive adversarial system not just entirely tear itself apart? Well, it's all thanks to something called a Nash equilibrium. This is a set of strategies where no agent has an incentive to unilaterally deviate. In these competitive cloud settings, agents actually train through self-play. They are constantly competing against increasingly skilled versions of themselves. Over time, through millions of interactions, these adversarial agents eventually find a perfect mathematical balance. They reach a point where no single agent can improve its outcome by changing its strategy alone. So by constantly outsmarting each other, they inadvertently maximize the total efficiency of the entire network. Pretty wild, right? Let's look ahead in Section 5, the future of cloud efficiency. Okay, so we've covered the physical cooling and the AI agents routing the traffic, but as demands continue to soar, the future is going to require some serious advanced cloud optimization. First, we're seeing the rise of hybrid heuristics. Remember those old, rigid rules we talked about earlier? Actually, scratch what I said about them being entirely in the past, because engineers are bringing them back, but combining them with deep learning. The old rules provide a fast, rough guess to start the process, which drastically speeds up the AI's initial training time. But the true frontier? That is quantum reinforcement learning. As cloud state spaces become unimaginably massive, traditional neural networks just require too much compute. By using quantum neural networks with quantum entanglement gates, these future AI models will process vastly more complex relationships simultaneously, using a fraction of the computational load and energy. Which really just leaves us with this incredibly provocative final thought. We are building these absolutely massive AI models that demand unprecedented amounts of data center energy. Yet, as we've explored today, the only way to effectively cool, schedule, and manage that massive energy consumption is by deploying even more AI. It's this fascinating, almost cyclical loop of modern infrastructure. It really makes you stop and think about the hidden physical costs of our digital lives. Ultimately, who or what is really running the cloud? Thanks so much for joining me on this explainer.